Hi, so today we're going to look at the HP4260A Universal Bridge. It's a very old instrument, originally designed and produced in Japan for the HP Yokogawa division. This was, I think, sometime in 1960s, maybe early 1960s. And actually, this is a very interesting instrument. It's a very basic principle of measuring resistances, capacitances, and inductances. And it uses the principle of the Wheatstone bridge. As you can see here, we have four devices, and I'll go through a little bit how this works. It's essentially a simple measurement, but in order to do capacitance and inductance measurements, it gets a little bit tricky, especially to get the bridge balanced, and we'll go through some of that. I'm not going to get into detailed mathematics of this. There's some very good papers as well as journal articles by the HP journal from I can give you the information later about which year and month, but it's actually described very well in there, at least for layman's understanding. So essentially what we have are four devices, devices, you can say either resistances, capacitances, or inductances, but in this particular example over here I'm going to start with the basic resistance measurement. Since this is a scalar measurement, there are no, you don't have to deal with vectors or phase angles and stuff like that, as long as the resistances are not too small or not too large, so in the neighborhood between few hundred milliohms to few megaohms. These assumptions do apply and are valid. So what we have here are the unknown resistance which you're trying to measure are unknown, and you have three other resistances inside the instrument, and that is Ra, Rb, and Rs. Now R unknown can have a large range, of course, going from several tens of milliohms all the way to several megaohms. So what we have is an Ra, which is the inside the instrument, which is like a coarse range selector, which you have to set to get to the right bridge null, and the null is really determined by the output over here, which goes into the electronics of the instrument. So what we do is apply a voltage across here between O and P, and that voltage depends on the value of the resistance it's trying to measure, of course. And you have an internal resistance, fixed one, which is Rs, which is I think 500 ohms. And then you have the Rb, which is the one you're manipulating on the dial of the instrument to get the null across this, to get the zero voltage between ground and this particular node over here. So all you're doing is tuning this value to basically balance the bridge, and you can see the equations over here on the right side, which tells you that Ra over Rs is the same as R unknown over Rb. So if you have a very large unknown, you can basically set the coarse range using Ra, which can be then stepped across to whatever value you want in that range, and then you'd use Rb to basically null out the bridge. So that's the way this works. So R unknown you can calculate to be Ra over Rs times Rb. So this is read off on the dial. When you adjust Rb, it directly reads on this output on the dial, which is like a rotating finely calibrated resistance, which is also a wonder by itself if you look at it. So that's this resistance measurement. I'll next describe the capacitance measurement, and the inductance measurement is very similar to the capacitance measurement. So let's look at that next, and then after that we'll do some measurements on various resistances and capacitors and see how good it is. The other thing we can do for the capacitor measurements and the inductance measurement is measure the dissipation factor, which is how much of the capacitor is an ideal capacitor versus it having some loss, and an inductor which can have a Q, which is how sharply it can be tuned, typically used for tuning purposes. You want to have a high Q or a low Q, that depends on the application. So these two things also can be measured on the instrument as a secondary measurement. So let's look at next the capacitor. Here we have the capacitance measurement, and there are two possible cases for capacitance measurements. One where you have a high dissipation factor, which is called the high D case. And then you have a low dissipation factor, which can be for very non-electrolytic caps which have very good insulation properties and have low leakage. So in this case, we are going to describe how a measurement for a high D case, and the bridge looks a little bit different over here. We have the unknown capacitor here, which is considered a CX, and RX it's its leakage parallel resistance leakage resistance, and then you have inside the instrument you have another combination of a parallel combination of capacitor and a resistor, the CT and RC. And then you have the same RB which we talked about in the resistance case, which is a variable resistor, which is the one that you're tuning, and this value is I think around 0 to 300 ohms or so. And you have RA, which is also the one we talked about, which has the range setting, which for different values of capacitors you can adjust the course change the RA value. So what we have is, of course, we need an AC signal to be applied into the bridge across O and P, and that AC voltage is a 1 kilohertz signal, and the value is internally it's adjusted inside the instrument to have a certain amplitude and so on. So as far as the bridge equations are concerned, it's very similar to the resistance case, except that now you have the capacitor and its reactance is 1 over Cx, proportional to 1 over Cx. And then the equation itself will be like 1 over Cx over Ra, this ratio, is equal to 1 over Ct divided by Rb. So you're tuning Rb and you're basically trying to null this bridge to get a zero indication. Now the Rc and the Rx add complications to that, because you can have various combinations of these values of Rc and Rx which you can get a null. So you may get a false null. If you don't get the capacitance equal and the resistance is equal over here, you could get null with different C and T ratio with different Rx and Rc ratio. So that's why the nulling of this thing is complicated. You have to adjust two variables to actually null this thing. So in the instrument there is a mechanism where there is auto capacitance measurement, where this Rc is actually controlled by the instrument automatically. And so all you have to do is to change Rb using the dial. So essentially you are ignoring the dissipation factor for this particular measurement. That's the instrument is controlling the Rc value, and then all you do is tune Rb to get this simplified Cx measurement. As far as the dissipation is concerned, what you do after you get the null, you then adjust Rc using another dial, which then you can basically try and get the best null possible after adjusting the C values close to where it should be. So you have dx equal to 1 over 2 pi f frequency 1 kilohertz Cx Rx is equal to 1 over 2 pi f CTRC, which is this particular bridge, this combination of C and R over here. This is tuned by adjusting Rc, so you get dx. Once you tune everything correctly, you have the same value for this particular combination of CXRX and CTRC. So that is a little bit more complicated measurement. I'll go through that. It's not as simple to see. When I first got the instrument, I was having difficulty getting the dissipation measurement done, but I think I can demonstrate that using a case where I can actually induce a dissipation factor which is quite high, and then you can use that to actually tune that very easily. Now we look at the theory of operation of this bridge. As you can see, it looks fairly complicated with all the circuitry around this bridge. Let me try and explain as the best as I can. So what we have here is the unknown resistor, capacitor in parallel, which is the unknown element. You're trying to measure predominantly the capacitance of this device. And the parasitic resistance is the leakage resistance, shown in parallel mode here. And then you have the bridge element over here, which is the tunable element, and manually controlled resistance that we have on the dial, which adjusts the value to get the capacitance into null. And then you have the fixed RA value, which is depending on the range selection, which depending on the value of C can be stepped up and down to get a course adjustment on the bridge. So when the AC voltage is applied here to a transformer, and that output of this particular bridge is also applied to the reference phase generator, which provides a phase reference from this particular AC waveform you want to compare against coming out of the bridge. So the output of the bridge goes to an amplifier, and then that is sent into a phase detector which compares the reference phase with the phase coming out of this particular bridge. The phase detector produces a voltage that is then amplified, and then it's sent through diodes whose resistance, AC resistance, varies as the current that flows through it. So in auto mode, when you're trying to get the capacitance value, assuming that the dissipation factor of the capacitance is small, you can use this technique to essentially balance the bridge. So this varying resistance is actually doing the function of the Rx RT in the previous capacitance measurement, and so it's automated by the loop over here. The phase detector maintains a certain quadrature phase between this and this signal to produce that tuning current, which basically adjusts the resistance, AC resistance of this particular diode, which then appears as a resistance across this particular capacitor, which then matches Rx over here. And essentially using that technique, you can now get at least the capacitance value nulled out, and then once you get the capacitance value nulled out, you can then switch this particular switch into the CP position, then tune RDQ, and then match Rx, and then you can essentially get a nulling of both the Rx, RDQ, as well as the previous measurement. Using this auto mode, you get the capacitance nulled out over here. So that essentially describes how this instrument works, and it's worth reading the paper by the Japanese Yokogawa team that developed this technique, and that is patented by that particular team, although the original idea to develop this came from the HP labs in the US. Before I get into some of the measurements, I want to show you the inside of the unit. Here's a top view. You can see a lot of the mechanical parts, the DQ switch control shown on the top, and then to the bottom is actually the CRL capacitor, the RB resistor tuning, and on the top you have some connectors which show where you can probe a few of the cards in there. This is the right side view that shows the large RB resistor, which is the resistor used to tune the capacitance, resistance, inductance value in the auto mode. This is a self-contained unit. You cannot be serviced or repaired or even modified. It's quite amazing how big it is and how well it works. This is again the top view with the J2 connector, which I'm probing the frequency adjustment pin. It was slightly off. It was reading 993 Hertz, and the voltage seemed okay. It should be between around 5 and 6.5 volts peak to peak. So I adjusted this value. I'm showing where to probe it. So after tuning the two resistors, you can see at the bottom right next to the red wire there are two red potentiometers. I basically tuned those and brought it to 1000 Hertz, and the voltage is 1.853 RMS, which is about 5.25 volts, which is well within the range it should be. Here you can see the gearing mechanism for the RB, the RCRL resistor, which is extremely complicated. It's quite a mechanical wonder, this whole instrument, with the TQ tuning, with the pulleys and the band over there which controls that, and then there's this gearing mechanism. So all in all, it's a complicated instrument, both electrically and mechanically, beautifully constructed. Okay, so here we have the instrument, and you can see it's fairly compact. It runs on AC, and right now let me describe the controls. So we have the input for the two terminals of the component you're trying to measure right here, the unknown, and there's a low terminal, and then there's just the high terminal, I guess. And you have an on-off switch. Then you have the DQ vernier with the vernier, which allows you to tune the dissipation versus or the Q, depending on whether you're doing a capacitor or an inductor. And here's the coarse range switch. which has right now in the resistance range will indicate kilo ohms and mega ohms and ohms and so on. And if you switch to the capacitance, you can see this is the parallel capacitance mode. Then you have finally you have the series capacitance mode over here. So, and then this is the auto mode where it will do the automatic capacitance measurement. And when you go into these two switches, you get into the dissipation factor for either for high dissipation or for low dissipation. Similarly, on the inductance side, you have the series inductance measurement, and then you have the parallel inductance measurement, and high Q parallel inductance measurement. So I'm not going to go much into the inductance measurement, although I can try a measurement, and I won't be able to confirm it very well, but we can try it, and then we'll just go through some resistance measurements, and also show you some techniques where you can use external amplifier to measure resistances which are out of its normal operating range, such as under 100 ohms or above 700K, I believe, where it has sensitivity issues by itself, so you need an external amplifier. So we'll try that. Then we'll look at some capacitance measurements with high and low dissipation, compare with the DE5000, which is a handheld meter, and see how they agree or not. And here we have the sensitivity knob, which allows you to increase the gain of the internal amplifiers, which I showed in the diagram. And here's the main tuning for this CRL. They call it the CRL control, capacitance, resistance, inductance, and so that is the variable RB resistance I talked about, and so we will use this to tune and null the bridge. So let's look at a resistor here. So what I have on the left over here, you can see that is a decade box, and right now this is a fairly accurate one. It's within few less than 1% or better in terms of accuracy, and we are measuring at the moment fairly large resistors, so I'm not too concerned about the lead resistances. So let's do this measurement here. I'm going to connect that in here over here. Right now it's the resistor mode, and you can see this is the decimal points right now for the resistance. So in the ohms mode, this is actually a 2K resistor over here. So right now it's indicating low, so I need to increase the value of this particular tuning resistance, the CRL, and I believe in this range it will not be able to null it, because this only goes up to 1030 or so, 1030, so it will go up to 1 kilo ohm. So I need to go to a higher range. So right now in the higher range, this is now reading 4.47 kilo ohms, and it's too high. So if we decrease this down, we should be able to see a null soon. You can see that it's actually coming into null, and it's very close to 1.99 kilo ohms, and that's very, very good. I mean, for an instrument that is probably, I'm guessing, about 45, at least 45 to 50 years maybe old. And actually you can increase the resistor, this sensitivity to, if the deflection is not quite enough for you, you can increase it. Right now it's at its max, so it's actually a very smooth null over here. It's not, you'll see the capacitance measurement has more slightly different behavior, so you get a null very close to 2K as measured over here. So now let me go down to a slightly lower value. Let's go to, this is 20 ohms now. So in this particular case you might have to actually have to use an external amplifier, but let me see if I can get a null on this one. So we know it's 20 ohms, so alright, so we are right there actually. So you can see yeah, it does deflect quite a bit, so it's probably good enough to do this directly on the instrument to get a good null. And right now at 20 ohms it's right on the money here, 199 probably. Now let's go down to 2 ohms. So this is 2 ohms, And you can see it's barely sensitive and at the maximum, so but it still manages to actually get a null, but it might be better to actually use an external nulling external amplifier. So let's try that. I'm going to set it up and then we will look at the output on an external amplifier. Alright, so I've connected this green wire to the green and black to the resistor. There is some lead inductance at this 2 ohms is going to be challenging, of course, with even having 1/10 of an ohm is going to be significant. And the red wire over here goes to my HP413, which is a voltmeter. This is one of the voltmeters actually that was in use around the time this particular instrument was developed, and they recommend using this as an external voltmeter. So anyway, you can see right now the bridge looks null to me, and it's barely difficult to, even with the max sensitivity, hard to tell whether this is right or wrong. It could be anywhere in this region, so it's very insensitive even with the max sensitivity. So let's look at the voltmeter here. You can see right now it's off scale. Not off scale, I mean it's deviating to the left. That means it's lower than what it should be. So let's try and tune this and see if I can bring it back to null on that. So this is on a 3 millivolt scale on that voltmeter. So I'm tuning the CRL knob gradually upwards, and once I'm done tuning it and get a null, I will come back and show you what I have. So it's now almost null there. So that I would say is total null, perfect null. So on the 3 millivolt scale, it actually managed to bring it into a 0 indication. So now let's look at the value that is on this CRL meter, which tells you the actual resistance I'm measuring. So it's reading 2.14 ohms or thereabouts. So I think this is fair to say that the resistance of these leads, total resistance, could be in the order of 140 milliohms. Fairly heavy wire, maybe 12 gauge for this particular measurement. And so I think this shows that using an external meter you can actually use this down to very low resistances, or perhaps even to the high resistance scale, which I haven't tried. You'll have the same issue with sensitivity when you go above a megohm or so. So that's the resistance measurement. Okay, so now we can do a capacitance measurement. I have one of those very low dissipation type capacitors. I think this is polystyrene, if I'm not mistaken. It's a very low value in the nanofarad. So we'll try and measure this. The first thing is we are going to be in the auto mode, as we said, to use the automatic let the instrument take care of the dissipation resistor by using that phase detector to control the current to the diodes and then set its resistance for that. Here it will be fairly high, so you don't have to worry about it, but for a different type of capacitor you might have to, it might come into play. So right now this is nanofarad. This is going to be, let's see if I can get any tuning on this. It's indicating this is already too high, so I need to go. Okay, so now it's indicating left. That means I need to decrease the value. And okay, there you go. You can see it actually switching between left and right about here. And you will not, it's difficult to see the null on this guy because, as I mentioned, it's only moves in one direction and it's a very sharp null. So it's about, I'm not sure what's going on here. Let me, okay, there we go. It's actually around 2.5 or so nanofarad. So if I can go into the picofarad, let's see if I can get anything on this scale. Probably too high for that value, so I may have to go into this scale here. So now it's in the 2 point something. Okay, so that's right there. So it's about 2.5. You can see that the null comes in very sharply and goes away. So you got to be it's very touchy for this particular measurement. So I would say it's about 2.59 something. Now you can increase the sensitivity to its maximum and then see if any change in the null occurs. That's as best as I can get. It's 2.59 nanofarad. So we look at this on the DE5000 capacitance tester, and let's see if I can get the D actually working. So I need to go into the low D here, and for that I need to also reduce the sensitivity so I can see some indication on this particular dial. So it's tough to see here, but you can zoom in further. Okay, that's as good as I can get it. So this is the bottom scale I'm looking at. The D factor is 0.007. I'll adjust this. You can see the needle barely moving over there. And as I bring it, this is 0.001, and that's actually a little bit, it's moved to the right, so that means I need to bring it a little bit higher. You'll see the needle moving to the left, and that means it's getting better as far as measurement is concerned. And then I go past 0.005, it's actually going back to the right. So the null is really, the D factor is roughly around here, is 0.003. That's the value of D it's reading as far as what it thinks it is. So we'll compare that with what the other instrument says, and then we'll do some other capacitors. So here's the capacitor, the same capacitor, using my Kelvin probes, and you can see on the reading over there 2.596, and we were reading 2.59, and the D factor is 0.003, whereas over here it's 0.0035. So as that's very, very accurate. You can see this pretty good for this old instrument, doing this kind of measurement without having been calibrated in decades, I'm guessing. Alright, so now I have a much larger capacitor, the same type. It's about 100 nanofarad. Again, I'm going to do the auto measurement to get the capacitance, and then we will look at the D factor again. So right now I've got to be in the nanofarad range. Let's see, let's try this. It's okay, so it's saying I need to be lower. So 190 nano, 170, 160, and okay, there you go. So it's about 90. So this is a minimum sensitivity, so I'm going to see if I can bring it to null right there. So this moves, but not this. It's still off scale, but at least you can see that it's so the value is probably closer to 95.5 or 95, so around 95 I would say. Okay, so it's about 95 nanofarad. So now let's do a D measurement. I'm going to go to the low D again and see if that works. So it's off scale again, and now we tune this again. So this is okay, 94.5, and now I'm going to try tuning this one to see if I can get a null, improve the null or make it worse. So it's getting worse over here. So if I go back to the left, it's getting better, and worse. So it's about here. So I'm guessing it's around 0.003 again, roughly 0.003, and a value of around 94. 0.5 or so nanofarad. Okay, I'm doing the same measurement on the DE5000. It's getting the same D value, 0.003, and 95 nanofarad, which was very close to what I originally got when I did the tuning on the auto mode for the capacitance. So again, very good results. Alright, so now I'm going to do something that helped me change the D value for the same capacitor and see whether this machine can read it. So what I've done is I put a 3K resistor in parallel with that capacitor, which is the same 100 nanofarad capacitor, and if you put a 3K resistor, the D will actually drop down, will go up to all the way to like 0.5 to 0.575. That's the value that the manual tells me it should be in the range of, and you can calculate that, just using some mathematics for the reactance and so on that is coming in parallel with this thing. So so right now, as you can see, the value of the capacitor still has not changed very much. It's still around 94.5 to 95. So that's one good thing. It does not get affected by the D if it's reasonably small. It's not terribly bad. D could be much worse, like 10 or 15, in which case this capacitance value read out to be wrong. It could be a little bit off. But now let's look at the high D case, in this case, and switch to this high D function and see what the D looks like here. So right now, again, this is off scale a little bit. So I'm going to bring this somewhat into tune and see if I can, what it happens to the D factor here. You can see it's actually improving. The value is coming closer to the left, getting better, and that's the peak over here, right about there. Okay, so that's the peak, and you can see from the reading on this second scale on top, right there, it's about 0.55, I would say. 0.6 is right here and 0.5 is right there. So it's about 0.55, which is close to what it's predicted to be, and it's still it's still reading the correct capacitance value. So it's kind of independent in the way it's actually measuring these two and not one affecting the other too much. Now let's look at the same results on the DE5000. Okay, alright, so here's this messy contraption where I've connected the 3K resistor across the capacitor and then feeding it into the DE5000. I'm going to turn it on. See what happens. So it's in auto mode. It should go to capacitance. It's doing CS now, but look at the value of the capacitor though. It's actually reading 125, and the D factor looks pretty correct to me. It matches almost exactly with the HP bridge, but the value of the capacitance is way off. And I tried, if I could go into CP mode over here, which should be the high D case, but it's actually not able to do that. So let me CS, and it's actually reading way off. So this is something I don't understand why it's off. Maybe the measurement technique here for high D is not quite there. It's not good for that. If somebody has any comments on this, it would be useful to know if I'm doing something wrong with this measurement here. But at least with the HP universal bridge, I was seeing no change in the capacitance value, and it was actually doing in CP mode. I can try it in CS mode and see what happens, but essentially I'm not getting the right value on the DE5000. So here's my final capacitance measurement. I have a 220 microfarad capacitor, electrolytic, and again I switched it to a higher microfarad range, and I'm doing the auto measurement again. So it's right now telling me at 165 it should be higher once. So let's go up. Sensitivity is set somewhat low, so I get some deflection here first, then I can tune that later. So 190. This is at 1 kilohertz, so these electrolytics are going to be sensitive to the frequency. They get better, higher values at lower frequencies. Let's look at this as I go. It's actually, yeah, changed to the other side. So the null appears to be at around 207 or so. You can see that's a pretty good null there. Now increase sensitivity will actually go off scale here. So it's very touchy at this point, but it's a good reading, I think. So you can see it's right there. 206.5 maybe. So that's about the value I'm getting. So we can compare this with the, let's do the D measurement, see if I can get something out of it. So let's do high D first, see if I can get something on that. Tune this guy. So it seems like the high D, so the high D is reading about 0.38 or so. 0.38. Okay, so I'm going to check against the DE5000 next. Okay, so this is the reading on the DE5000. The value for the D is very close to what I got, 38 or so. And here's 3.374. Whereas the capacitance is quite a bit higher. I'm getting around 230 microfarad instead of the 206 or so. So I don't know. Based on the previous measurement, I tend to trust this particular meter, the HP, because of its fact, it doesn't get affected by the D factor as much, whereas this one tends to read high when the D factor is high. So I think there's something to do with the way this measurement is going on. It's not clear to me. So yeah, so it's 0.375. That's what I'm seeing here. So this was a long video. Sorry if I bored anyone, but essentially we looked at this HP4260A. I covered the fundamentals of bridge RLC measurements using this universal bridge from HP. This is developed by the HP Yokogawa Japanese group in the 60s. The HP4260A proved to be very accurate in my opinion, and it was simple to use, especially for capacitor or inductor measurements, which I didn't get into, with the simplified tuning procedure where the instrument took care of the dissipation factor, or in the case of inductance, the quality factor Q, into auto tuning mode, so you didn't have to worry about setting two variables to get it, and could do these measurements fairly quickly. Now the resistance mode measurements were very straightforward. All you had to do is tune it up and down until you got the null, and then it had good sensitivity for most measurements except when it was too small or when it's too high. I demonstrated using an external voltmeter HP413A for small resistances to get a better null indication. It did not have issues with high dissipation factors affecting the capacitance value measurement, unlike the DE or DE5000, unless I did something wrong in using the DE5000 or used the meter incorrectly. Okay, I did get into the inductance measurements. As it is, this video was very long, so if I have a good inductor, I'll probably try it out later. But I think the main point was to really prove that the capacitance measurements worked, and inductance is very similar measurement. Essentially, it's a different reactance. That's all. There are other features which I didn't get into, and one is that it can use an external frequency source to do measurements at other frequencies from like 20 Hertz all the way up to, I think, several tens of kilohertz, if I'm not mistaken. So if you're interested in low frequency, like for electrolytics, you can do that with this. And the other thing you can do is to also do biased capacitance measurements using a DC bias on a capacitor and getting the capacitance for that, and similar for inductance, I'm sure. So that's all I have for this video. Hope it was useful. See you next time. Thank you. Bye.